specialist program. And last summer, I did a work study with Professor John Percy, where we investigated a potential theoretical cause for this phenomenon in red giants called long secondary period. And this cause was known as the eclipsing binary hypothesis or the eclipse hypothesis. So red giants are unstable to low order pulsation modes, generally in the fundamental and or the first orbital mode. And they're found to pulsate, which causes fluctuations in their brightness, which we can identify by analyzing the light curves that we get from observing these stars. So we see them as sort of periodic changes in a sort of sinusoidal pattern in these light curves, and we expect to see them when we're analyzing the light curves that we see from red giants. But we research red giants more specifically because they're actually quite common in our universe, so they're quite literally all over the place. And they are actually also a future evolutionary phase of stars, much like our own sun. So about a third of these really common stars experience or undergo this phenomena. It's important to learn about it and to learn about what causes it, which is what we focused on in our work. So in about a third of red giants, as I mentioned, we see this normal pulsation period as we would expect. But then upon further inspection, we also see this second periodic pattern superimposed on the normal pulsation period. This is what came to be known as the long secondary period, or LSP. So as you can see here, we have a light curve with that was created through a time series analysis. So it extracted the LSP from the normal pulsation light curve that we see from the red giant. So you can see the magnitude on the y-axis and time in modified Julian days on the x on the left, and then on the right you can see the phase curve that was extracted also from this light curve using time series analysis. And the LSPs tend to be about 5 to 10 times smaller than their normal pulsation period. So as mentioned, the theory that we investigated for the cause of this phenomenon was called the eclipsing binary theory. So to do this, we analyzed the light and phase curves for stars with known LSPs that we selected from a catalog that was made the summer prior by another undergraduate student who's now doing her PhD at Marseille, her name is Sandra Zakova. And this plot on the right that I'm showing you here shows the brightness on Y and time on the X, but this is what a quote unquote like normal eclipsing binary light curve would look like. So you can see that the larger star covering the companion has more of an effect than when the companion, smaller stars covering that larger star. But these curves are very different from the light curves that we would see for LSPs, but that's due to the hypothesized geometry and structure of the eclipsing system as well. So we tend to see more rounded curves rather than these like linearly defined curves that you're seeing. The data that we used for our analysis was from the American Association of Variable Star Observers, or the AAVSO, and the data set that we used also had about 100 years worth of observations, with the entirety having optical observations, which you can see here on the light curve for star U, del, and black. And then for the last 30 to 40 years of observations, they were also collecting Johnson V photoelectric data, which you can see illustrated here in green. And then the red is just a four-third polynomial that we fit some of the data to try to infer some physical patterns. We chose 11 stars from the catalog, and we chose them just mostly based on their LSP amplitudes. So the bigger the amplitude and the more data we have, the easier it is to infer anything physical about the system. Because if you can think we don't have enough data, or if the LSP amplitude is just too small, when we analyze these curves, it's really hard to see different patterns and like shapes in it. So we also used VSTAR, which is a time series analysis software, to create plots like the one you see here on the screen. And this allows us to use time series analysis to like extract the LSP from the normal pulsation period, so that we know that when we're looking at like a phase plot, for example, we know it's only the LSP and it's not also the normal pulsation period. So this analysis is really important because, as I mentioned before, red giant stars are quite common and are a future evolutionary phase of stars like our sun. But according to the hypothesis that our analysis is also testing, which was proposed by Szpigiel in 2021, which is still our current best explanation for LSPs, but the theory proposes that the red giant is in a companion with a brown dwarf or low mass star that began as a planet. So it requires a bit more knowledge about planet formation, or it can help inform about planet formation, which is really important. And it also hypothesizes that the companion is enshrouded in dust. So it requires that process of accretion of dust as well around the companion, which would be great to know more about. So if we can understand LSPs really well, it can be sort of like the gateway to understanding these other two concepts really well. And it's a mystery. So who doesn't like solving a fun astronomical mystery? So some of the predicted causes of LSPs include the eclipsing binary theory, which I've mentioned once or twice now, which is basically that the red giant star is in an eclipsing binary with a low mass, thus enshrouded companion. And this was proposed by Eber's in 2021. You can see here on the right, we have an artist's conception from the paper that proposed the hypothesis. And this artist's conception was made by his 12-year-old niece, Matilda, which I think is quite incredible for a 12-year-old. And another theory that's also floating around the field is that the LSP appears throughout the red giant's evolution. So it appears between the red giant branch and the asymptotic red giant branch. But for our analysis, we focused more on trying to either analyzing data and seeing if it supported or was maybe more against the eclipsing hypothesis, the eclipsing binary hypothesis. So the two main questions that we had the goals of answering were, can we find evidence for this eclipsing binary hypothesis? And since we had such a unique data set that was on the time scale of decades, almost a century actually, we were also investigating whether this LSP phenomenon and the geometry of the structures changed over time. So we're going to start to see if we can find some evidence for this eclipsing binary hypothesis theory. So, as I said, I visually analyzed 11 different light and phase curves for 11 different red giant stars. And we all know they have known LSPs. So here, for example, I'm showing you a phase plot for a star called Udell. There were two main stars in our analysis that had large LSP amplitudes and prominent patterns, like the one that you see here. So it was easier and also possible to infer anything physical about the system using these two stars. So we're seeing the brightness and magnitude on the y and the phase on the x-axis. And we analyzed the entirety of the data sets. Note that also the light curves from this data set, again, it was the time on the x-axis, but all of the time is in modified Julian days. So we use the time series, we basically feed it the LSP, which we take from that other catalog. So for Udell, the LSP had a duration of 1,179 days. And then we pick a sort of epoch in time and we create a phase curve from that. And then we can use the phase curve to infer some of the geometries from the system. So to infer these actual geometries of the system for the eclipse, we basically look at it and you can look and see there are clear variations in brightness here because there's a curve that goes through different magnitudes, but then you also might notice a bit more upon further inspection about the shape of the curve itself. So as I mentioned, we analyzed two main stars and the maxima for both of them are rounded, but the minima actually had different shapes, which we inferred was actually a physical, like a result of the physical system and not just something that the phase curves happen to have. So Udell has a rounded minima, which implies a system that looks a little bit more like this. So the minima being rounded sort of implies physically that we would expect a more solid or relatively small companion, but this is including the dust, so it's not just the object itself, but also the dust that surrounds it. And that's just because it would spend more time behind the star, so that minima would have a longer duration. Whereas if we had a different phase plot with a pointed minima, so this is the other star that we analyzed mainly, but this is Wyland. It has an LSP of 1,245 days. And as you can see here, clearly it has that pointed minima instead of the rounded one that the other one had. And we inferred that this was because the star was likely more transparent and relatively larger. These are both relative to the red giant that it's in a binary with. So it would just spend less time fully behind the red giant. So if you can imagine, it would just like go behind and then it would slowly come back around. Because it's just bigger, like half of it would be behind. So we would see that as a minima in phase curve. However, there is one more thing about the hypothesis that I've kind of been keeping from you until now, and that's that the companion actually also is hypothesized to have a dust tail following it. So if you look, I included it in these drawings that I showed you, and it was included in the artist's conception as well. And we actually also found evidence for this dust tail. So basically we have this low mass object, the companion, it's enshrouded in dust, but then it also has like a tail of dust that follows it as it orbits around the red giant star. So to actually physically infer the dust tail, we kind of took a look at these phase plots. We're like, why do they not look like normal sinusoids? As you can see, they have that sort of like slow ingress and then a quick decline, and that pattern just repeats throughout the entire data set that we have. And we inferred that it was because the system might actually look a little something like this. So you would imagine as the red giant began to be covered by the companion, it would slowly become dimmer and dimmer, so we're just getting less light from the red giant. And then as the object itself would move like around the star, the dust tail would still be covering it, so it still wouldn't get its like full luminosity, so to speak. And then as the object comes back around, the dust tail finally leaves, which is that quick decline that we see in that moment where the red giant is fully luminous, let's say. And then the object will come back around and start eclipsing it again, and it will start that slow ingress once again. So that was what we inferred from the actual shape of the phase curves. Now, I've actually only mentioned 2 of the 11 stars that we analyzed, and that's because the other 9 looked a little bit more like this in the sense that they maybe didn't have as much data, or they just had small amplitude LSPs. So you can see that there's evidence of some sort of eclipsing binary, like there's something going on that's not from the normal pulsation, but it's just pretty hard to infer anything physical about the system. These look like normal sinusoids, which we know they might not be because of the evidence that we found for the dust tail and stuff like that. So we did analyze the other 9 stars, but they just had phase and light curves that looked a little bit more like this, so they just didn't have as much data to physically infer from. And then we had another aspect of the project, which was analyzing whether this LSP phenomenon changed over a time scale of decades. And we did that using a weighted wavelet analysis. So we were plotting the semi-amplitude of the LSPs here on the Y against the time, again in modified Julian data on the X. This is the weighted wavelet analysis we did for UDEL, which was that first phase plot that I showed you with the rounded minima. And the semi-amplitude of UDEL increased by about a factor of 2. The biggest, like most significant change that we had was that one of them increased by a factor of 8. But when we're working with timescales that are on the order of, I think we had a data set that had about 82 years, which is quite a long time, like not astronomically, but for astronomical data. We just attribute these significant changes to be due to dust variation, since the system is hypothesized to have a dust enshrouded companion and with the dust tail following the object. We would expect there to be some variation over time scales this long. So that's what we kind of attributed these changes in the semi-amplitude to. So there were 2 main conclusions from this analysis, and they were that we did in fact find strong evidence for the eclipsing binary theory for the cause of LSPs, and that this phenomenon and like the geometry of the system and the system itself does not change over time. So thank you, and I'm happy to take any questions.
Melanie.
Maybe I don't understand how the secondary period is overlaid, but would it be easier to find these in red giants that don't have a primary periodicity?
If I'm not mistaken, I believe most red giants do have primary periodicity, and I think if it didn't have that pulsation, it might be difficult to realize that it was the LSP and not the primary pulsation, because if you don't have both, it's hard to distinguish them. The only way I could think of would be just the length of the period of the
On that, I think you said it, but I sort of still at the beginning, how did you separate it? Because you said you were plotting 2 forms you saw along.
Yes.
So how did you remove the time series?
So as far as my understanding goes, we used time series analysis. The software that we had basically asked us to put in a period that we wanted to see like the shape for, and we had the LSP value. So we put in the LSP value, and then it showed us the phase curve for that specific period. So since we knew what it was, it isolated sort of for the LSP, not include pulsation.
I think the other signal is still in there, that's why it's so correct.
So it's still there, you don't like divide out the normal one, that's why like the black points are above.
Yeah.
Yes.
Maybe you already mentioned this, but what would evidence that like refute the first the eclipsing binary theory look like?
I think if we found, like, maybe if it was more sinusoid, like if it was a strictly sinusoidal curve, we wouldn't be able to infer the dust tail, so that would be evidence against that aspect of the theory. Or if like, it was found to be like a light curve that looked more, like this one, then there's no dust surrounding the object, because this would be much more obvious that it was just the object orbiting the red giant. I don't know what evidence would look like if there was no binary at all. Someone proposed that this also could be because of tidal effects that the companion might have or something like that with the red giant. And I don't have evidence to refute that, but this was the theory that we think the evidence.
I guess historically, there's. All of the data are in one passband. Is that correct?
I think so.
But going forward. I suppose one could, well, these amateurs are well equipped now, they
Yeah.
could. Observe with 5 filters or something, would that. Help learn something about the dust?
It might be able to, because if we can observe in different bands, we can also see if there are different geometries to the systems in the different bands and see if maybe one of them attributes to like a curve that looks more like this, so then maybe it doesn't have any dust and the other ones just weren't precise enough to take the measurements, but I do not know the extent of the effects it would have to measure the different bands.
I think you're guessing at this, in the infrared dust would be more
Yeah.
transparent, right? So you would see this.
You would see it a lot more clearly. I think that would be a really interesting analysis.
Do you know if there's any variable polarization with my company? Of obscuring part of the star or having that dust scattering? All over the ground.
I don't think I can. Sorry. I can't look.
Maybe I'll ask one final one, because you mentioned that a lot of the time the theory here is that these are low mass. Yes. Companions, like how low should I be thinking? I know recently. Beetlejuice also has, exactly along that theory period that it was put forth that, 18 solar mass star and the constraints on the possible companion there are now like less than solar mass or so. Like how low,
It's been found,
what?
that's been actually imaged that.
Yes, at like 2 sigma, but I agree with you. I like it. Yeah. But yeah, it's about a solar mass, like something like that, probably 3 main sequence star, like how low mass do we think these are? You have a sense?
I don't know, I can imagine they can't be that low because they still have to have an effect on the red giant itself.
Yeah.
Not just from the, like, the companion has to have a component as well, the object.
Yeah.
But. Yeah, I don't know the relations, but I don't think the catalog that we had included the masses, so that's just very.
Great, this is excellent. Okay, let's switch back to your.